There you go.
So I'm going to start by talking a little bit about neural networks, because I went to a talk yesterday by somebody who is working presently at Los Alamos. I don't know if he's always been at Los Alamos. I'm looking for his name, because I forget names pretty easily. Kenyon. So his name is Kenyon. And his first name is Garrett, so I'll just put a G there. And what he was saying is something is a huge extension of what I was suspecting when I said that that I thought that brains work in a different way, somewhat differently from the way in which neural networks work. And the standard neural network has some sort of input coming in. You have a bunch of neurons, and then neurons in quotes, and they feed forward. Everything is feed forward. And then you have another layer perhaps, and so forth, and then you finally have output. It turns out that in real brains, you have three things that are different. First of all, you have crosstalk in the same layer. So within a given layer, you will have, by the way, why do I say layer? Well, the brain, let's suppose we start with the eye. So we've got a retina here, which has, I think it's something like 100 million cells, actually, rods and cones. And they're sending signals back, and let's see, what did I want to say? All right, I forgot what I was going to say there. There's also something else that's happening with in real brains. Namely, the signals don't just go like that. Some of the signals go backwards. So you have lateral transmission, and you have backwards transmission, as well as forwards transmission. Also, and now I remember what I was going to say. So you have these various stages, and at some point you have branching. And what happens here is this is specialized. So in other words, the cells here are concerned with a particular aspect of vision, and it might be an edge, a line, it might be a circle, it might be that something's moving, and then other ones are controlling the focusing of the eye and the coordination between one eye and the other for 3D vision. And as you go along, it becomes even more specialized. And in fact, during a therapy of a patient who had serious epilepsy, the patient agreed to be part of a study while the physicians were trying to cure her or his epilepsy. And they were placing an electrode on various neurons, and the patient would report what he or she saw. Turned out that they found that there was one neuron, and I'm not very good with names, that they call the Halle Berry. She's an actress. Okay. Did I spell it right?
I think it's pronounced Halle Berry.
Yeah, it is.
Halle Berry?
Yeah.
Okay. Halle Berry. She's actually in a film that a set of TV shows that I rather like that's on either Amazon or Netflix called Excellent. And it's actually a series about AI in a sense. And I thought it was better than most of the content on Netflix and Amazon. Anyway, this person had a single neuron that would respond to images of Halle Berry. And so what was happening there was a particular neuron, and they had a microelectrode that was insulated everywhere except at the tip, and then this went to some sort of a detector. And then they would show the patient various images, and there'd be no signal at all unless they showed the patient an image of Halle Berry, and it didn't matter what image. It could be an image in which there was a crowd of people, and one of them was Halle Berry, or it could be Halle Berry, a full shot of the whole head to toe, or it could be a close-up of the face. And no matter what it was, and it could be at any angle. Well, I don't know, maybe not upside down, but any normal position. And that image would fire, but that neuron would fire, but not in the other case. So, and what Kenyon has been doing is building neural networks that have lateral crosstalk as well as forward feeding of impulses. And he finds that he gets better results with that technique. It's probably also true that if you include back propagation as well as forward propagation of information, and if you arrange for the neurons to become more specialized as you go to higher layers. That's another thing here, is that these things are often in layers. And in fact, the cortex, where we do our heavy-duty thinking, or higher level thinking, it's something like a square foot in area, but it's very thin. It's a millimeter or a couple of millimeters thick only. I put a link on the class website to a book that's free, written by a man named Hubel, who won the Nobel Prize in physiology. And by the way, this book could also be, I hope I put a link to this book also on the Physical English class website, because this guy Hubel is an example of excellent scientific writing. So let's see, what else did I want to say? Yeah, let me just say a few things about neurons. So I'm going to try to draw a neuron. This is not going to be Boyle's greatest neuron. There are about 50 different kinds of neurons, and they vary enormously. What typically you have is of course an axon that looks sort of like this, and then it has split ends. I don't know much about split ends, but I once had a girlfriend who complained that she had split ends. I didn't know what they were. Apparently it's, well, anyway, what happens in a real axon is that this thing separates into hundreds or thousands of split ends. And so this is called the axon. This is called the cell body. And this is also called a Latin word, soma, which I guess means body. And then it also has things that look like trees, called dendrites. The Greek word for tree is dendron, and so you can see why they use that term. And there might be one from the other side that does a similar thing. Now, what's important is that axons from other, or split ends of axons from other neurons come in like this. And they make contact on the dendrites. So the dendrites are kind of the ears of a neuron. They don't look like ears. Now, so there's a cell body. Cell body, which has, of course, the nucleus and all the organelles. Most of the organelles, some of the mitochondria are in the axon, dendrites. So these things are called dendrites. And there are 10 to the 2 to 10 to the 3rd. Well, let me just mention the axon again for the absent student. You have an axon coming out, and then it splits into hundreds of split ends, which then touch dendrites of other cells, other neurons. Moreover, there would be 100 or 1,000 other neurons that send out their axons, 100 or 1,000 axons, which then split into mini or micro axons, and those micro axons almost make contact with the dendrites of a particular neuron. So a particular neuron is feeling hundreds of input signals and is sending out one output signal to hundreds or thousands of other cells. And now right here, I said almost makes contact, and that's because what you have there is a synapse. And so what's happening is there's this micro axon, or split end, split end of an axon that comes down, and in a gap of about 20 nanometers, there's a gap of about 20 nanometers between it and the surface of the dendrite. And this is called a synapse, of course. And the synapse then is only 20 nanometers wide. And of course, apart from the cells, you've got, I guess it's called cerebrospinal fluid. Anyway, whatever the fluid is there in the brain. And that fluid is mostly water and then various salts. Sodium chloride, potassium chloride, calcium chloride, magnesium chloride, all kinds of salts. And of course, complicated organic molecules. And now what happens here is that when the electrical impulse, well, of course, this signal that goes along the axon is an electrical impulse. When that electrical impulse gets down here, a receptor cell is sensitive to it, and that receptor cell releases, as I recall, releases calcium ions. Okay, wait a minute. I left something out. The electrical impulse comes down, and when the electrical impulse gets to the tip, it releases many neurotransmitter molecules, which are able to diffuse randomly across the 20 nanometer gap. I say randomly. It may be that they are charged and are attracted by an electric field. In any event, so there's a neurotransmitters go across, and those neurotransmitters are then grabbed by essentially protein molecules called receptors that receive the neurotransmitter, and when they receive the neurotransmitter, they send a signal across. So you've got the surface of a neuron, like the surface of any cell, is about 5 nanometers thick. And so you've got a protein that goes through called a receptor protein, and it grabs it receives the neurotransmitter molecule and then sends a signal through. And then that signal changes the electrical potential across the surface of the postsynaptic neuron, the dendrite of the postsynaptic neuron. And these various pharmaceutical drugs, what they do is they interfere with the neurotransmitters. And I think one of them is serotonin. Anyway, and God knows what the opioids do. Don't want to talk about that. So that's sort of the picture. Well, there's one other part of the picture that's very important, especially to physicists, and that is what this signal is. Well, we've got this surface here of the axon, which is a membrane that is, as I said, 5 nanometers thick. And what it's composed of is molecules that are basically, the chain here is lots of CH2s, so it's essentially fat. Fat is CH2. And then a head group, and there are various head groups, and they involve a phosphate group, and these things are called phospholipids. Lipid is the fancy word for fat. And okay, so this is the is just a general cell membrane, but there are special things in a cell membrane. There are, in fact, remarkably, there are all kinds of remarkable things that are only beginning to be understood. Proteins going across, and some of them are, for example, sodium-potassium pumps. And these sodium-potassium pumps pump sodium in, and they pump potassium out. Okay. On the other hand, there are also some leak channels. And these are rather remote. These are, again, protein molecules, so I should draw them like that. But, so these are... So you have potassium leak channels. And because of this situation here, what you've got is the pumps, the sodium-potassium pumps, try to keep a balance between the sodium and potassium inside and outside, but the potassium leaks out. The result is you have negative charge here positive charge here. And the potential across here is of the order of 50 millivolts typically. For nerve cells, it's 70 millivolts. And the electric field points in. So the voltage is positive outside, negative inside. Now, what happens is that there are also sodium channels. So this is a sodium channel, or a sodium pore. Word of pore and channel are used somewhat interchangeably. Now, the potassium channels, most of them remain open all the time. Some of them are sensitive to the voltage across the membrane. And by the way, because this is only 5 nanometers thick, the electric field in the membrane is of the order of megavolts per meter. That's because the thing is 70 millivolts, but it's only 5 nanometers. That's 5 10 to the minus 9. And so, what happens is these sodium channels are closed normally when the potential across the membrane is 70 millivolts, electric field pointing in. However, if a signal comes along that depolarizes this to some extent and brings it down from 70 to a lower value, maybe 40 or so, the sodium channel's open. The sodium concentration outside the cell is high, and so sodium ions rush in. And that flips the potential to something like 40 millivolts with positive being inside and negative outside. Once the potential is flipped, though, the sodium channels close and they only stay open for 10 to the minus 3 seconds. And when the cell is depolarized and then reverse polarized, more of the potassium channels open, the sodium channels close, and so the thing goes back to normal. So as a function of time, what you have for the voltage is minus 70, resting state, then a depolarization, and then you shoot up to some value that's positive for only 1,000th of a second, and then it shoots back down to minus 70. And this is, okay. Now, the other thing is that once the sodium channel has opened, it, and then closed after 1,000th of a second, it can't open again for another 1,000th of a second. And in fact, typically for longer than that. And so this depolarization signal causes the sodium channels on this side to open, but not the ones on this side, because they can't open until another 1,000th of a second goes by. The result is the signal goes across, and the signal moves pretty fast because, after all, our reflexes or our reaction times are less than 1/10 of a second, and yet some of our neurons are 1 meter or 2 meters long, tall. Bairn has ones that are 2 meters long. Okay, so that's pretty much what I wanted to say. This field, by the way, of biophysics is a rapidly developing field, and lots of jobs, and it's also a field where you can be pretty sure that you're going to be doing no harm. Whereas other areas of physics, you could be a large fraction of the jobs involve making weapons of mass destruction or minor destruction. And of course, another area that's rapidly developing is artificial intelligence. But the message from Garrett Kenyon yesterday in the talk he gave over in the math department was that the people doing AI would make more progress if they made their artificial intelligence computers more like actual brains. And I think he's absolutely right. And I think that means that there's a whole interesting, really interesting area where you have a confluence of AI on the one side and brain research on the other. And putting the two together strikes me as just a marvelous field for young people to go into. And it seems to me the job situation is as positive as it is negative in high-energy theoretical physics. There were many areas of pure science because the funding across the whole field of science has been monotonically decreasing as a fraction of the federal budget for the past 50 years. The only part that's held its own is medicine. And to some extent, astronomy has done better than the rest of physics, but most of the astronomy money, of course, has been wasted on sending fighter pilots to the moon or to a crate flying in low and high Earth's atmosphere around the planet. Okay, so much. What?
I didn't say anything. I didn't say anything.
Oh. All right, so let's see. Maybe I should just review a couple of things then with regard to, we'll switch now back to path integrals. So what we used was, let us say, Q double prime, or let us say maybe Q1, Q0 is, well, first of all, QP is e to the I QP over the square root of 2 pi h bar. So that's the inner product of an eigenstate of momentum and with an eigenstate of position. And the idea here is that if Q is the operator and Q prime is an eigenstate, then the eigenvalue is Q prime. And if P is the momentum operator, then P prime is the eigenstate, P prime the eigenvalue, and or ket P prime is the eigenstate. And, anyway, those are the relations. The basic commutation relation is QP is I H bar. And what we found last time was we found formulas for these matrix elements, and in fact what we found was that if you the time evolution operator is a unitary operator, which is an exponential of a Hermitian operator, the energy operator, the Hamiltonian, divided by h bar multiplied by the time difference. So this amplitude then is the probability amplitude that if the particle is at Q0 at time 0, that it turns out to be at some point Q sub t at time t, where this means the particle's at Q sub t and this means the particle's at Q sub 0. and that's the amplitude. And this thing is then a path integral, which is an integral of the action of all processes divided by h bar, and it's written conventionally dq, meaning capital D, meaning that one integrates over all processes. This s square bracket q means that s is a functional of the function q. Q is a function of time. So SQ is an integral of the Lagrangian of Q of t dt. And in this case, since I've already used t for the time interval, this would be t prime 0 to t. And this big D, if we're serious about it, oh, where did I write what big T was? Hold on. Yeah, all right, hold on. Here we are. This is so what we're doing here to actually compute the thing is, to approximate this integral, is we divide the interval 0 to t into intervals 0 to epsilon, epsilon to 2 epsilon, dot, dot, dot. Finally, n epsilon, here n minus 1 epsilon to n epsilon, which is the same thing as n minus 1 epsilon t. And that's just so we divide this interval 0 to t into n subintervals, all of them very short, and we integrate then over all the q's. And this action is typically, so this S of q, let me write it again here. S of q then is right. Let's do it this way. An integral, well, not an, it's a sum actually. Hold on, let me get my eraser. It's epsilon times the sum, j equals 0 to n minus 1, 1/2 m, and now q dot is qj dot squared minus v of qj. So that's S of q, and we have to integrate over these n values of qj, or actually it's n minus 1 values of qj we integrate over. We integrate over them from minus infinity to plus infinity. And here, qj dot is actually qj plus 1 minus qj divided by epsilon. So that's the picture. And this seems, and in fact it must have seemed to everybody who thought about it to be implausibly complicated and unstable, implausibly mathematically unstable, because you're taking a limit as n goes to infinity of this quantity here, and we're doing infinitely many integrals, and everything is just has an I here. There's no damping. But
I have a question.
yeah,
So where are these segments of time being used? You break up the period of time into small
right.
segments.
0 to t we break up into n intervals.
And then you're summing over those intervals, or where are those intervals?
We're summing over. We're summing. Well, we can only do a finite number of integrals on a computer.
Yeah.
So we decide we're going to do n of them. And so then we have to approximate. See, the real S of q is an integral of q of, say, m over 2
okay.
q dot squared minus b. So we approximate that as epsilon being the length of each interval times the value of the Lagrangian in that interval. And that value depends upon the values of q at the two ends of the interval. So that's the approximation. Now, to tell you the truth, I don't know if anybody's actually done this on a computer. What people have done on a computer is the one that I did first in the last class, namely the case where you're not trying to do e to the minus I th over h bar, but you were trying instead to do the Boltzmann operator, which is e to the minus h over kt. Because there's no I, everything is damped, and people do that on a computer a lot. Actually, a graduate student and I are thinking about playing around with this, but we haven't yet gotten really serious. On the other hand, it does make mathematical sense because I derived for you what, what we start out with actually is not this. We start out, of course, with, let me just remind you what we start out with. We start out for the first interval, it's from q, it's q e to the minus I epsilon h over h bar q0. We start out with that, and we insert a complete set of states. And that's q1 p. P is an eigenvector. Well, we write that. Shall I repeat this business, or have you seen it too often for me to repeat it?
You can repeat it.
All right, hold on. Let me get a full piece of chalk then. Also, you asked a question, so here's your candy. So let me do this in maybe a little more detail. This is e to the minus I epsilon p squared over 2m, because h, in the simplest case, is p squared over 2m plus v of q, where q is the position operator and p is the momentum operator. And we then have these eigenstates. And p integrates from minus infinity to plus infinity. Because this is an eigenstate of that operator, this is integral well, I'm using p for the same, in other words, this p is the operator, this p is an eigenvalue. And so this now is the eigenvalue squared over 2m. This q is the operator, this is the eigenvalue, and now in this case, it is different, so it's v of q0. And then we have these inner products, q1, p, q0. And those inner products are the ones that I wrote down earlier. In other words, we use this formula, which is basic quantum mechanical result. And so this is equal to integral dp e to the minus I p squared over 2m minus I epsilon b at q0, and this is just a constant. And then this is e to the I p q1 minus q0 over, there are two factors, so it's not a square root, it's actually 2 pi h1. I hope that's what I wrote. No, I did get it right. Okay, so now we look in the integral tables for this integral over p. And even though everything here is an I, it's an I here and an I there, and it's actually divide by h bar. Oh, I forgot to divide by h bar. So now if we do this integral, this turns out to be m over 2 pi I epsilon to the 1/2 e to the I epsilon times m q0 dot squared over 2 minus v of q0, where of course I'm using this convenient notation here. And now we see that if we put a bunch of these together, these factors just add, and they add up like that.
Okay.
So that's the picture. Now, what Feynman pointed out long ago was that not only does this make sense, but it's easy to approximate these path integrals. Because, and it's especially easy to approximate, well, it's easy to approximate the path integrals when the potential V is quadratic. And the reason is that we can write the arbitrary function q of t. So what we're supposed to do here is integrate over all processes, and this is the classical action of the process. We're supposed to integrate over all processes. Well, we can write an arbitrary process as a classical process plus a departure from the classical process. And so what we can do in general is we can write then that S of Q is S of Q classical plus delta Q. And in this case, this part of the process splits nicely because it becomes an integral dt of a half m q classical dot plus delta q dot squared minus v of q classical plus delta q. So that's what we have to integrate. And now, what we know is that since this is the classical process, if we expand this in powers of delta q, the first order term vanishes. That's the principle of stationary action. Or equivalently, that's what we use to define the classical process. So that means that the total action is the action of the classical process plus things that are second order in delta Q. Second or higher order in delta Q. Of course, nobody said delta Q was small. Okay, go.
So what's that O? Or
Oh, you know, it's a funny thing. I never really was taught what these big and small O's are. But in physics class, one always just says of the order of. And mathematicians have
Oh.
big O and small o, and they mean something very specific by that. In physics departments, we just mean order of the square of that.
Okay.
Okay. Now, the problem, however, is that that we're supposed to integrate over all processes, and so consequently, if this is the classical process, this could be an arbitrary deviation from the classical process. However, this thing here is a process that goes from 0 to 0, so it's a loop in Q space, because both Q of t and Q classical of t go from Q0 to Qt in time t. So this guy vanishes at t equals 0 and at t. All right, now, it turns out, however, that if this thing is quadratic, then this expansion is simpler. It's S of Q classical plus, in other words, when we expand this, of course, the linear term goes, the quadratic term remains. And if this is quadratic, the linear term goes, the quadratic term is just there. And so that is nothing more than S of delta Q. But now delta Q doesn't have any information about Q in it anymore, or about where this is just the integral of a process that goes from the origin back to the origin. And so consequently, the total path integral, which would be Q sub t e to the minus I th over h bar Q sub 0, is then the classical action times the path integral over all the loops for the quadratic case. So V quadratic. And this thing is independent of Q0 and independent of Q of t, so it's just a function of what's left, h bar and t, and parameters in the Hamiltonian. And so, so this thing in general then is some function, loop integral of time, e to the I s of Q classical over h bar. So in other words, we've got a formula for the total path integral that for the case of quadratic potentials is exact, but we don't know what L is. On the other hand, we can figure out what L is, or at least make a very good guess, which turns out to be right, just by realizing that the limit t going to 0 of qt e to the minus I th over h bar q0 is just nothing more than qt q0, and that's three-dimensional delta, or one, whatever, however many dimensions it is, of qt minus q0, because these are orthogonal states, and this turns into just the identity operator as t goes to 0. And so you then choose L of t so that the limit of this thing is that, and that gives you the right answer. And in particular for a free particle, what we saw last time was that Q e to the minus I h t over h bar 0. m over 2 pi I h quote t 3x e to the I m q squared over 2h quote t. And this is exact. And so in other words, the whole business makes sense. It's just that it took somebody who was remarkably perceptive and really good at doing integrals and figuring out mathematical relationships, and somebody who was also encouraged in speculative directions by his thesis advisor, Wheeler. Wheeler was very much a blue sky man, and so Feynman went ahead with this. Dirac and Schwinger probably guessed at some of this, but didn't move ahead because I guess they were doing other things or they just didn't see the point. But Feynman did, and so we can do the same thing in the case of the Boltzmann operator, and then actually, let me give you another example of this. Let's consider the Bohm-Aharonov effect. Have you guys heard about that? All right, this is a very interesting quantum mechanical effect. And it was proposed by Bohm and Aharonov. Bohm, I think, was actually chased out of the United States by McCarthy. Joseph McCarthy, not Eugene. Eugene was a good guy. But Joseph was really a bad guy. Anyway, what they suggested was this. Suppose you have a beam of electrons and you send it past a cylinder or a solenoid, for that matter. Make it a solenoid pointing out of the blackboard with wires going around it, so it makes a huge B field inside and not much outside. And so you have these electrons going past, and then you have a detector here, and theoretical physics detector, and you move the detector around, you vary the magnetic field, you vary the velocity of the particles and so forth. And let's use the path integral to figure out to analyze this experiment. It turns out path integrals are just marvelous for doing some things, not so great for doing other things. It's one of the things that it's very nice to do. First of all, what's the action here? Well, the action is 1/2 m. Well, of course, it is v squared, but we can write v squared as v times, or rather dt times v squared as v dot dx. So this can be v, and, or let me do it in 2 steps. So this is the classical action for a charged particle of mass m moving with speed v in a magnetic field described simply by the vector potential, no electrostatic field. But now we write v dt as dx, and so this becomes integral 1/2 m v dot dx. And here v dt becomes dx, so this is q a dot dx. And altogether then we can write this as a spatial, a line integral in space of 1/2 mv plus a dot dx. So that's the classical action for an electron that goes, say, from, did I use specific numbers? All right, from some x0 to some x1, or if you want x0 to x of t. Or if you want to use Q's, then maybe I should have stayed with Q because I was talking Q. Q and X are the same, okay? They're both position. Okay, so this is the integral. And now we remember that the main factor is just the classical action, at least when the thing is quadratic. And since A is a fixed, for each experiment, or each moment of each experiment, A is fixed. This is quadratic in B, so we can use this expression where this is just some L of T. And consequently, what we have here, the phase is the classical action. And now there are two ways, there are two basic processes. There's the process like that, and then there's the process like that, and we have to add them together. But the difference of the two, the phase difference, is just the loop integral around the solenoid. And I think I should switch now to the whiteboard because I'm out of space. Maybe we'll try to. Okay, so what is the phase shift? Of course, we divide by h bar and it's delta s. And so this then is a loop integral of mv over 2 plus qa dot dx over h bar. And so this is the loop integral of mv dot dx over 2h bar plus q over h bar integral, well, the integral of a dx around the loop. So this is the loop. A dot dx around the loop is the same thing as the integral of b dot ds, the integral of the magnetic field over the surface, enclosed in the loop. Because B is the curl of A. So the integral of the curl of A over the surface is the integral of A around the loop. So that's the integral of B dot ds. So this is the integral of B dot ds. And this is what we call the flux. And so this is equal to mv dot dx over 2h bar plus q over h bar times magnetic flux through the solenoid. And the experiments have been done and verified this. And so what you can do you have the detector in a particular place, and so what should happen is that this is the phase, and this is the phase difference of the two paths. If the phase difference is pi, they should cancel. And if it's 2 pi or 2n pi, they add. And so when the flux, the condition then for interference, so interference or zero counts in the detector would be q over h bar times the flux to be n pi, where pi is an integer. And so that would mean that the magnetic flux through the solenoid would be n pi h bar over q. And so they would, and in particular then, if you change the flux by an amount that was given by n, you should go from one interference pattern to the same interference pattern. And so they've shown that those experiments have been done, and those were the results that they found. Now, for the case of the Boltzmann operator for a free particle, we use this formula for the delta function. It's a limit t going to 0, m over 2 pi h bar t 3/2 e to the minus m q squared over 2 h bar t, and this is delta cubed of q. And so for a free particle, once again, the action is quadratic, and so q e to the minus h over kt 0 is then, I'll just give you the final answer, mkt over 2 pi h bar squared 3/2 e to the minus mkt q vector squared over 2h bar squared. So that's that particular. And once you have this matrix element, you can compute the Boltzmann, the partition function, well, for a free particle isn't that big a deal, I guess. But the same technique can be used in more complicated situations. And in fact, when you're dealing with approximating e to the minus h over kt, this is something that works very well on a computer because of the minus sign there. Exponential damping. All right, let me say a few things about quantum field theory in 8 minutes. What we start out with is quantum mechanics, and if we have many q's, so many particles, what we'd say is the commutator of qi with pj would be I h bar, but now Kronecker delta ij. In other words, the q2 commutes with p3, but it doesn't commute with p2. And so that's the basic rule. And of course, you also have qi, qj, 0, pi, pj, 0. Now, the transition that is generally made to field theory is that we replace the ith quantum mechanical variable by a field at a particular point, which we might call x sub I. And of course, this is also a function of time, and so we could call it x sub I at time, t. And if one is doing, if you put space on a lattice and time on a lattice, then what you have is you have a a finite set of q's for a given spatial area or volume, then you have a finite set of variables, and we call these the quantum fields. But what's always done is we always go to the limit in which x is a continuous variable. So we have one quantum, we have infinitely many q's in effect, and we call them the field at, so this thing goes to the quantum field at position x and time t is just to be thought of as one of the q's in this original scheme. And the pi's, pj of t goes to what we would normally call this pi of x of t, and in simple theories, this turns out to be the time derivative of phi at x and t. And then the analog of this relation is what's called an equal time commutation relation. I guess there's an h bar, but I set h bar equal to 1 so often that I'm looking for it, I can never find it. So instead of the Kronecker delta, delta ij, we say a three-dimensional delta function, delta of x minus y. But this is where the times are the same. And so now we can repeat all the stuff that I did earlier for these for the patterns. We can do exactly the same thing for fields, and then what we get is essentially this phi. Well, let me jump to a notation that is almost universal. This function, phi, this field, phi of x and t, is, at least if the field is real, it's a Hermitian operator. So it has eigenvectors, a complete set of eigenvectors. And in fact, that's just phi of x. And so this has an eigenvector which I'll write this way. And in fact, what I might, okay, so this is the eigenvector of the field, but notice that just as the q's commute for different I and j, so too the fields at different points of space, but at the same time, commute. So you can have a simultaneous eigenvector of phi of x and phi of y at the same time. So consequently, this thing is really a simultaneous eigenvector of the field at every point in space at a given time. Now, some people make the mistake of thinking that these are states of moderate energy. In fact, they're states of absurdly high energy. And you can see why that's true, because if you just ask about a state of an eigenstate of the position operator in ordinary one-dimensional quantum mechanics. That state, Q, is an integral of e to the I kx over all, and I'll put in a square root of 2 pi, and I'll leave out h bar. It's an integral over all momenta to have position precisely defined. So the energy of this state is the energy of a linear combination of states of all momenta. That means it's infinite energy. And in this case, this is true in spades of this function, of this state. So it's possible that use of this language may have led people in the wrong direction in quantum field theory, but it's a standard thing people do. Anyway, if you go ahead and do that, what you find is that e to the minus I ht over h bar, say phi prime, phi double prime, this is then an integral e to the I s of all processes divided by h bar. The classical action of all processes, integrated now over all field configurations that go from phi double prime to phi prime in this interval 0 to t. And there may be some constant out here. And in the case, instead of the Boltzmann operator, what you have is a minus s, and the s is, it's something that looks like the energy, but really isn't, because it's a derivative of the field, not with respect to time, but with respect to energy, or imaginary time. It's a, I'm not quite sure what English word to associate with it. Anyway. All right, so I guess we're done. So to repeat, we're going to skip class on Tuesday, no makeup class. Thursday, those of you who want to present for presentations can. I think maybe you should turn the thing on.